Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. Glaciers are large, persistent bodies of dense ice that form over many centuries through the gradual accumulation and compaction of snow, and they are found on every continent except Australia, covering approximately 10% of the Earth's land surface, which amounts to roughly 15 million square kilometers of ice at the present time. The study of glaciers, known as glaciology, has been conducted in a systematic manner since the 18th century, though the fundamental processes by which glaciers form, move, and reshape the landscape beneath them were not fully understood until well into the 20th century. It is estimated that glaciers and ice sheets together contain approximately 69% of the world's freshwater, a figure that is often cited in introductory geology textbooks and repeated here for the sake of completeness. The formation of a glacier begins with the accumulation of snow in a location where more snow falls during the winter months than melts during the summer months, a condition that is met in polar regions at high elevations, and in certain maritime climates where precipitation is abundant and temperatures remain sufficiently low. When snow first falls, it is a loose, hexagonal crystalline structure with a density of approximately 50 to 70 kilograms per cubic meter, which is considerably less dense than liquid water at 1,000 kilograms per cubic meter. Over the course of days and weeks, the delicate points of individual snowflakes begin to sublimate and refreeze, rounding the crystals into smaller, more compact grains. This aged snow, which has survived at least one summer melt season without completely disappearing, is referred to as Firn, a term derived from the German language. And Firn has a density that typically ranges from 400 to 830 kilograms per cubic meter. The transformation from firn to glacial ice is a process that may require anywhere from several decades to several centuries, depending on the rate of accumulation and the temperature conditions at the site. As additional layers of snow and firn are deposited on top of existing layers, the increasing overburden pressure causes the air spaces between the ice grains to diminish progressively. At a depth of approximately 40 to 80 meters, depending on local conditions, the interconnected air passages between grains are sealed off, trapping bubbles of ancient atmosphere within the ice. At this point, the material has reached a density of approximately 830 kilograms per cubic meter and is classified as glacial ice. Pure glacial ice, which has been subjected to sufficient pressure over a long enough period of time, has a density of approximately 917 kilograms per cubic meter, which is the maximum density that ice can achieve under normal surface pressure conditions. The process of firnification, as it is sometimes called in the glaciological literature, is influenced by several factors including temperature, the rate of snow accumulation, and the amount of meltwater that percolates through the snowpack. In regions with warmer temperatures, such as the coastal mountains of Norway or the maritime glaciers of New Zealand, meltwater percolation can accelerate the densification process considerably, as liquid water fills air spaces and refreezes. bonding grains together more rapidly than pressure alone would accomplish. In contrast, in the extremely cold interior of the Antarctic ice sheet, where surface temperatures may average -57 degrees Celsius and virtually no surface melting occurs, the transformation from snow to ice may require several thousand years, as the process is driven entirely by the slow mechanical compaction under the weight of overlying snow. Glaciers are classified into several distinct types based on their morphology, their relationship to the underlying topography, and their thermal characteristics. Valley glaciers, which are also referred to as alpine glaciers or mountain glaciers, are elongated streams of ice that flow downhill through pre-existing river valleys, typically originating from a bowl-shaped depression called a cirque at the head of the valley. These glaciers range in length from less than 1 kilometer to more than 100 kilometers, and they are found in mountain ranges throughout the world, including the Alps, the Himalayas, the Andes, the Rocky Mountains, the Southern Alps of New Zealand, and the mountains of Scandinavia. The Aletsch Glacier in Switzerland, which is approximately 23 kilometers in length as of recent measurements, is the longest glacier in the European Alps, though it has been retreating steadily since the mid-19th century. Ice sheets are the largest type of glacier, defined as continuous masses of glacial ice that cover an area of at least 50,000 square kilometers. At present, there are only two ice sheets on Earth: the Antarctic ice sheet and the Greenland ice sheet. The Antarctic ice sheet is by far the larger of the two, covering an area of approximately 14 million square kilometers, which is roughly the size of the contiguous United States and Mexico combined. It contains approximately 26.5 million cubic kilometers of ice, which represents approximately 90% of all the ice on Earth and approximately 70% of all the fresh water on the planet. If the Antarctic ice sheet were to melt entirely, which is not anticipated to occur in the foreseeable future under any but the most extreme climate scenarios, global sea levels would rise by approximately 58 meters. The Greenland ice sheet covers an area of approximately 1.7 million square kilometers and contains approximately 2.85 million cubic kilometers of ice. Its complete melting would contribute approximately 7.2 meters to global sea level rise. The Greenland ice sheet reaches a maximum thickness of approximately 3,368 meters at its thickest point, which was determined through radio echo sounding measurements conducted during the mid-20th century and subsequently refined by more recent surveys. The bedrock beneath the Greenland ice sheet has been depressed by the immense weight of the overlying ice, and in some locations the bed surface lies below present-day sea level, a phenomenon known as isostatic depression that is also observed beneath the Antarctic ice sheet. Ice caps are smaller versions of ice sheets, covering less than 50,000 square kilometers, and they are typically dome-shaped masses of ice that overwhelm the underlying topography, flowing outward in all directions from the highest point of the dome. Notable ice caps include the Vatnajökull ice cap in Iceland, which covers approximately 8,100 square kilometers and is the largest ice cap in Europe by volume, and the Devon ice cap in the Canadian Arctic, which covers approximately 14,400 square kilometers. Ice caps are found in Iceland, Svalbard, the Canadian Arctic Islands, the Russian Arctic Islands, and in various subantarctic islands. Piedmont glaciers form when valley glaciers emerge from the confines of mountain valleys onto relatively flat lowland areas, where the ice spreads out into broad, fan-shaped or lobate masses. The Malaspina Glacier in Alaska is perhaps the most well-known example of a Piedmont glacier, covering an area of approximately 3,900 square kilometers, where it spreads across the coastal plain between the St. Elias Mountains and the Gulf of Alaska. The Malaspina Glacier is so large that its full extent can only be appreciated from satellite imagery or from very high altitude, and it has been the subject of numerous scientific studies since the late 19th century. Tidewater glaciers are glaciers that terminate in the ocean, calving icebergs from their fronts into the sea. These glaciers are found in coastal regions of Alaska, Greenland, Svalbard, Patagonia, and Antarctica, and they are of particular scientific interest because they are sensitive indicators of both oceanic and atmospheric conditions. The Columbia Glacier in Alaska, which has been retreating dramatically since the early 1980s, losing more than 20 kilometers of its length, is one of the most intensively studied tidewater glaciers in the world. The calving of icebergs from tidewater glacier fronts is a significant mechanism of ice loss and contributes to sea level rise in addition to the melting of glacial ice by warm ocean waters that circulate beneath the floating portions of these glaciers. The mass balance of a glacier is a fundamental concept in glaciology that describes the net gain or loss of ice over a specified period, typically 1 year. The mass balance is determined by the difference between accumulation, which includes all processes that add mass to the glacier such as snowfall, avalanching, wind-blown snow deposition, and the refreezing of meltwater and ablation, which includes all processes that remove mass from the glacier such as melting, sublimation, calving of icebergs, and wind erosion of snow from the glacier surface. When accumulation exceeds ablation over the course of a year, the glacier is said to have a positive mass balance and will tend to advance or thicken. When ablation exceeds accumulation, the glacier has a negative mass balance and will tend to retreat or thin. The equilibrium line altitude, commonly abbreviated as ELA, is the elevation on a glacier at which accumulation exactly balances ablation over the course of a year. Above the equilibrium line altitude lies the accumulation zone, where the glacier gains more mass than it loses, and the surface is typically covered with snow and firn throughout the year. Below the equilibrium line altitude lies the ablation zone, where the glacier loses more mass than it gains, and the surface often consists of bare glacial ice during the summer months. The ratio of the accumulation area to the total area of the glacier, known as the accumulation area ratio, or AAR, is a useful indicator of glacier health. A typical healthy glacier in a state of equilibrium has an accumulation area ratio of approximately 0.6 to 0.7, meaning that 60 to 70% of the glacier's surface area lies within the accumulation zone. The equilibrium line altitude varies considerably from glacier to glacier and from region to region, depending on local climate conditions. In the tropical Andes, the equilibrium line altitude may be found at elevations of approximately 5,000 to 5,500 meters above sea level, while in maritime climates, such as those found in southern Norway or southeastern Alaska, the equilibrium line altitude may be as low as 1,000 to 1,500 meters above sea level. In the polar regions, the equilibrium line altitude can be at or very near sea level, which is why glaciers in places such as Svalbard and the Antarctic Peninsula can extend to the coastline. The measurement of glacier mass balance has been conducted using a variety of methods over the years. The traditional glaciological method involves placing a network of stakes drilled into the ice surface at various locations across the glacier, measuring the emergence or burial of these stakes at regular intervals, and combining these point measurements with snow density data to calculate the mass change at each location. These point measurements are then extrapolated across the glacier surface to determine the total mass balance. This method has been applied continuously to several dozen glaciers around the world since the 1940s and 1950s, providing some of the longest continuous records of glacier change available to science. The Storglacieren in northern Sweden, for example, has had its mass balance measured every year since 1946, making it the glacier with the longest continuous mass balance record in the world. More recently, geodetic methods have been employed to measure glacier mass balance over larger areas and longer time periods. These methods involve comparing topographic maps or digital elevation models of a glacier surface from different dates to determine the volume change of the glacier, which is then converted to mass change using an assumed or measured density. Satellite gravimetry, particularly data from the Gravity Recovery and Climate Experiment, known as GRACE, which was launched in 2002, and its successor GRACE follow-on, launched in 2018, has enabled scientists to measure mass changes of entire ice sheets and glacier regions with unprecedented precision. GRACE data have revealed that the Greenland ice sheet lost mass at a rate of approximately 286 gigatons per year between 2002 and 2020, while the Antarctic ice sheet lost mass at a rate of approximately 150 gigatons per year during the same period, though with considerable interannual variability. The study of glacier mass balance is not merely an academic exercise, as it has direct implications for water resources, sea level rise, and the understanding of climate change. Many rivers in Asia, South America, and Europe receive a significant portion of their summer flow from the melting of glaciers, and changes in glacier mass balance can therefore affect the water supply for hundreds of millions of people who depend on these rivers for drinking water, irrigation, and hydroelectric power generation. The Ganges, Indus, and Brahmaputra river systems, which together support the livelihoods of more than 1 billion people, receive varying but significant contributions from glacial meltwater, particularly during the dry season when other sources of runoff are diminished. The global inventory of glaciers, maintained by the World Glacier Monitoring Service based in Zurich, Switzerland, catalogs more than 215,000 glaciers worldwide, excluding the two ice sheets. These glaciers cover a total area of approximately 726,000 square kilometers, and they are distributed across all continents except Australia, though the vast majority of glacial ice by volume is concentrated in the polar regions and in the high mountain ranges of Asia. The Randolph Glacier Inventory, which was compiled specifically to support assessments of global glacier change and sea level rise, provides detailed outlines of every glacier on Earth and has been an invaluable resource for the glaciological community since its initial release in 2012. It is worth noting in the context of this discussion that the terminology surrounding glaciers and ice masses can be somewhat confusing to the uninitiated. The term glacier is sometimes used loosely to refer to any large body of ice, but in strict glaciological usage, a glacier is a body of ice that deforms and flows under its own weight. Snowfields and ice patches that do not flow are not considered glaciers, even though they may persist from year to year and may superficially resemble small glaciers. Rock glaciers, which are masses of rock debris cemented together by ice that flow slowly downhill, occupy a somewhat ambiguous position in glaciological classification, as they exhibit flow behavior similar to true glaciers, but consist predominantly of rock rather than ice. The distribution of glaciers across the Earth's surface is controlled primarily by temperature and precipitation patterns. Glaciers require both sufficiently cold temperatures to preserve snow and ice from one year to the next and sufficient precipitation to build up the ice mass over time. This is why some of the coldest places on Earth, such as the dry valleys of Antarctica, where precipitation is extremely low, are essentially free of glacial ice, while comparatively mild maritime regions such as southeastern Alaska and southern Chile support extensive glacier systems due to their very high precipitation rates. The relationship between temperature and precipitation in controlling glacier distribution was recognized by the early glaciologists of the 19th century and has been refined through quantitative analysis in the decades since. The Antarctic ice sheet is conventionally divided into three distinct sectors: the East Antarctic ice sheet, the West Antarctic ice sheet, and the Antarctic Peninsula ice sheet. The East Antarctic ice sheet is by far the largest of the three, containing approximately 21.7 million cubic kilometers of ice and resting on a bed that is predominantly above sea level, a fact that makes it relatively stable compared to its western counterpart. The West Antarctic ice sheet, which contains approximately 3.3 million cubic kilometers of ice, rests on a bed that is largely below sea level, a configuration that makes it potentially vulnerable to a process known as marine ice sheet instability, in which the retreat of the grounding line into deeper water leads to increased ice discharge and further retreat in a self-reinforcing feedback loop. The potential for rapid destabilization of the West Antarctic ice sheet has been a subject of intense scientific investigation and concern, particularly since observations in the early 21st century revealed that several of its major outlet glaciers, including the Thwaites Glacier and the Pine Island Glacier, were thinning and accelerating at rates that exceeded the predictions of most ice sheet models. The physical properties of glacial ice are worth considering in some detail, as they determine many aspects of glacier behavior. Pure ice has a density of 917 kilograms per cubic meter at 0 degrees Celsius and atmospheric pressure, which is approximately 8% less dense than liquid water at the same temperature, a fact that explains why ice floats on water and why icebergs project above the sea surface. The crystal structure of ice that forms under normal conditions, known as ice IH, is hexagonal, and the weakness of the bonds between the basal planes of this hexagonal structure is what allows ice crystals to deform relatively easily through the glide of dislocations along these planes, a process that is fundamental to glacier flow, as will be discussed in greater detail in subsequent portions of this narration. The thermal properties of ice are also important for understanding glacier behavior. The specific heat capacity of ice is approximately 2,090 joules per kilogram per degree Celsius, which is approximately half that of liquid water. The thermal conductivity of ice is approximately 2.2 watts per meter per degree Celsius, which means that temperature changes at the surface of a glacier propagate downward into the ice relatively slowly. In the Greenland ice sheet, for example, the cold temperatures of the most recent glacial period are still preserved in the deep ice, because the thermal diffusion timescale for an ice sheet 3 kilometers thick is on the order of tens of thousands of years. The latent heat of fusion of ice, which is 334 kilojoules per kilogram, means that a considerable amount of energy is required to melt ice. And this is one of the reasons why glaciers can persist in environments where the mean annual temperature is above the freezing point, provided that sufficient snowfall compensates for the summer melting. The color of glacial ice is another property that merits a brief mention. Fresh snow appears white because it scatters all wavelengths of visible light more or less equally, but as snow is compacted into firn and eventually into glacial ice, the air bubbles that scatter light become progressively smaller and fewer, and the ice begins to absorb red wavelengths of light preferentially, transmitting and scattering blue wavelengths more effectively. This is why deep glacial ice, and particularly the walls of crevasses and the faces of calving glaciers, often display a striking deep blue color. The blue color of glacial ice has been the subject of scientific investigation since at least the 19th century, and the explanation in terms of the selective absorption of red light by ice was first proposed by the physicist John Tyndall in 1872. The stratigraphic record preserved within glacial ice has proven to be one of the most valuable archives of past climate conditions available to science. Ice cores drilled from the Greenland and Antarctic ice sheets contain a continuous record of past atmospheric composition, temperature, volcanic activity, dust loading, and other environmental parameters extending back hundreds of thousands of years. The Vostok ice core from Antarctica, which was completed in 1998 and reached a depth of 3,623 meters, provided a record of climate and atmospheric composition extending back approximately 420,000 years. Subsequently, the Epica Dome sea ice core, also from Antarctica, extended this record to approximately 800,000 years. These ice cores have revealed the intimate coupling between atmospheric carbon dioxide concentrations and global temperature over glacial interglacial cycles, with carbon dioxide levels varying from approximately 180 parts per million during glacial periods to approximately 280 parts per million during interglacial periods, values that are well below the current atmospheric concentration of over 420 parts per million. The oxygen isotope composition of the ice in these cores, which is determined by the ratio of oxygen 18 to oxygen 16 in the water molecules, serves as a proxy for the temperature at the time the snow fell. Because the fractionation of oxygen isotopes during evaporation and condensation is temperature dependent. By measuring the oxygen isotope ratio at successive depths in an ice core, scientists can reconstruct a continuous record of past temperature changes with remarkable precision. Air bubbles trapped in the ice preserve samples of the ancient atmosphere, which can be analyzed to determine the concentrations of greenhouse gases, such as carbon dioxide and methane at the time the bubbles were sealed. Layers of volcanic ash and sulfuric acid aerosols record the timing and magnitude of past volcanic eruptions, while dust particles indicate changes in atmospheric circulation and aridity in distant source regions. The movement of glaciers, which is to say the slow, inexorable flow of ice from regions of higher elevation to regions of lower elevation, or from the interior of an ice sheet toward its margins, is governed by several distinct physical mechanisms, each of which has been the subject of extensive theoretical and experimental investigation over the past century and a half. The fact that glaciers move at all was not universally accepted by the scientific community until the mid-19th century, when systematic measurements conducted by researchers such as Louis Agassiz and James David Forbes in the Swiss Alps demonstrated conclusively that glacier ice is not a static mass, but a flowing substance, albeit one that flows at rates so slow as to be imperceptible to the casual observer. The primary mechanism by which glacier ice moves is internal deformation, also known as plastic flow or creep. This process occurs because ice, despite its apparent rigidity at the human scale, behaves as a viscoplastic material when subjected to sustained stress over long periods of time. At the molecular level, ice crystals deform through the movement of dislocations along the basal planes of the hexagonal crystal lattice, a process that is analogous to the slip of atoms along crystallographic planes in metals and other crystalline materials. The rate at which ice deforms under stress is described by Glen's flow law, which was formulated by the British physicist John W. Glen in 1955 based on laboratory experiments in which he subjected small samples of polycrystalline ice to known stresses and measured the resulting strain rates. Glenn's flow law states that the strain rate of ice is proportional to the applied stress raised to a power n, where n is an empirically determined exponent that has a value of approximately 3 for the range of stresses typically found in glaciers. This means that if the stress applied to the ice is doubled, the rate of deformation increases by a factor of approximately 8, which is 2 raised to the third power. The flow law also includes a temperature-dependent parameter known as the rate factor or flow parameter, which increases exponentially with temperature according to an Arrhenius-type relationship. This temperature dependence means that warmer ice deforms much more readily than colder ice, and as a consequence, the deeper portions of a glacier, where the ice is warmed by geothermal heat from the Earth's interior and by the frictional heat generated by the deformation process itself, tend to flow faster than the colder surface layers. The stress that drives internal deformation in a glacier is the gravitational shear stress, which arises from the component of the glacier's weight that acts parallel to the bed surface. This shear stress increases with both the thickness of the ice and the surface slope of the glacier, a relationship that can be expressed mathematically as the product of the ice density, the gravitational acceleration, the ice thickness, and the sine of the surface slope angle. For a typical valley glacier with a thickness of 200 meters and a surface slope of 5 degrees, the basal shear stress is approximately 100 kilopascals, which is a value that is commonly observed in glaciers around the world and is sometimes referred to as the yield stress of glacier ice, though this terminology is not strictly accurate given the viscoplastic nature of ice deformation. The velocity profile that results from internal deformation alone shows the maximum velocity at the surface of the glacier and decreasing velocity with depth, reaching zero at the bed if the glacier is frozen to its bed. This is because the shear stress increases linearly with depth, and the cumulative effect of the deformation at each level is added to the deformation of all the layers below. The mathematical integration of Glenn's flow law over the thickness of the glacier yields a velocity profile that varies as the fourth power of depth for the case, where n equals 3. Which means that the majority of the ice deformation is concentrated in the lower portions of the glacier where the shear stress is highest. In practice, this means that the upper portion of the glacier, sometimes referred to as the brittle zone, is carried along passively by the deforming ice below, much as a raft is carried along by the flowing water beneath it. The second major mechanism of glacier movement is basal sliding, which occurs when the base of the glacier slides over the underlying bedrock or sediment. Basal sliding can only occur when the ice at the base of the glacier is at the pressure melting point, which is the temperature at which ice melts under the pressure exerted by the overlying ice column. For a glacier that is 200 meters thick, the pressure melting point is depressed by approximately 0.15 degrees Celsius below 0 degrees Celsius, a small but physically significant reduction. Glaciers in which the basal ice is at the pressure melting point are referred to as warm-based or temperate glaciers, and basal sliding can account for a substantial fraction of their total movement, in some cases contributing 50% or more of the surface velocity. The process of basal sliding itself involves two sub-mechanisms that operate at different spatial scales. The first is regelation, which is the process by which ice melts on the upstream side of small obstacles on the bed, such as rock bumps with dimensions of centimeters to decimeters, flows around the obstacle as a thin film of water, and refreezes on the downstream side. This process is driven by the pressure difference between the upstream and downstream sides of the obstacle, which causes the melting point to be lowered on the high-pressure upstream side and raised on the low-pressure downstream side. The latent heat released by refreezing on the downstream side is conducted through the obstacle to the upstream side, where it provides the energy needed for melting. Regelation is most effective for small obstacles because the heat must be conducted through the obstacle, and the rate of heat conduction decreases as the size of the obstacle increases. The second sub-mechanism of basal sliding is enhanced creep, which is the intensified plastic deformation of the ice around larger obstacles on the bed, such as rock bumps with dimensions of meters to tens of meters. Because the stress is concentrated around these larger obstacles, the ice deforms more rapidly in their vicinity than it would in the absence of the obstacle, effectively flowing around them. Enhanced creep is more effective for larger obstacles because the stress concentration extends over a greater volume of ice, whereas regelation becomes inefficient for large obstacles due to the longer heat conduction path. There exists a critical obstacle size, known as the controlling obstacle size, at which the combined effect of regelation and enhanced creep is minimized, and this size is typically on the order of 0.5 to 1 meter for typical glacier conditions. It is the obstacles near this controlling size that offer the greatest resistance to basal sliding. The presence of water at the base of a glacier has a profound influence on the rate of basal sliding. Subglacial water, which originates from surface meltwater that penetrates to the bed through crevasses and moulins, from basal melting due to geothermal heat and frictional heating, and from groundwater discharge, forms a thin film or a network of cavities and channels at the ice bed interface. When water pressure at the bed approaches the overburden pressure of the overlying ice, the effective normal stress on the bed is reduced, which diminishes the friction between the ice and the bed and allows the glacier to slide more rapidly. Seasonal variations in basal water pressure, which are driven by variations in surface meltwater production, can cause significant seasonal variations in glacier velocity, with faster flow typically observed during the early summer when meltwater input is high, but the subglacial drainage system has not yet developed an efficient channel network. The third mechanism of glacier movement, which is relevant in cases where the glacier rests on a bed composed of unconsolidated sediment rather than bedrock, is subglacial deformation, also known as bed deformation or till deformation. In this mechanism, the sediment beneath the glacier is itself deforming under the shear stress transmitted through the ice, and the glacier is carried along on top of this deforming layer, much as a conveyor belt carries objects placed upon it. The importance of subglacial deformation as a mechanism of glacier movement was not widely appreciated until the 1980s, when borehole measurements and seismic studies revealed that a layer of soft, water-saturated sediment, known as deformation till, underlies substantial portions of some glaciers and ice streams. The rate at which glaciers move varies enormously, from less than a few meters per year for small, cold-based glaciers in polar regions, to several kilometers per year for fast-flowing outlet glaciers and ice streams. The Jakobshavn-Isbrae in Greenland, which is one of the fastest-flowing glaciers in the world, was measured to have velocities exceeding 46 meters per day, or approximately 17 kilometers per year, at its calving front in 2012 and 2013. The speed of Jakobshavn-Isbrae has varied considerably over the observational record, having accelerated substantially in the early 2000s before slowing somewhat in recent years, a pattern that has been attributed to changes in ocean temperatures and the retreat of the calving front. Ice streams are fast-flowing corridors of ice within an ice sheet that are bounded on their sides by slower-moving ice rather than by rock walls, as is the case for valley glaciers. The ice streams of the West Antarctic ice sheet, such as the Whillans, Cam, Bin-Shadler, Mackayl, and Eckelmeyer ice streams, which drain into the Ross Ice Shelf, have been particularly well studied. These ice streams flow at velocities of several hundred meters per year, which is 1 to 2 orders of magnitude faster than the surrounding ice, despite having very low surface slopes. The rapid flow of these ice streams is facilitated by the presence of a layer of weak, water-saturated subglacial sediment that offers very little resistance to the overlying ice. The Cam ice stream, formerly known as Ice Stream C, ceased its rapid flow approximately 160 years ago and is currently nearly stagnant, a phenomenon that has been attributed to the diversion of subglacial water away from its bed, which caused the subglacial sediment to strengthen. Surging glaciers are glaciers that alternate between long periods of relatively slow flow, known as the quiescent phase, and brief periods of dramatically accelerated flow, known as the surge phase. During a surge, which typically lasts from 1 to 3 years, the glacier may advance by several kilometers, and its velocity may increase by a factor of 10 to 100 or more. Surging behavior has been observed in glaciers in Alaska, Svalbard, Iceland, the Karakoram Range, and several other regions, though the majority of glaciers worldwide do not exhibit surging behavior. The causes of glacier surges are not fully understood, but 2 main hypotheses have been proposed. The hydrological switching hypothesis suggests that surges are triggered by a reorganization of the subglacial drainage system from an efficient channelized configuration to an inefficient distributed configuration, which raises water pressure and reduces bed friction. The thermal switching hypothesis, which is more applicable to polythermal glaciers in subpolar regions, suggests that surges occur when the bed of the glacier warms to the pressure melting point, allowing basal sliding to commence. The surface of a flowing glacier is subjected to stresses that can cause it to fracture, producing features known as crevasses. Crevasses form in zones of extending flow, where the ice is being stretched, and they are oriented perpendicular to the direction of maximum tensile stress. In the central portion of a valley glacier, where the ice flows faster than along the margins due to friction with the valley walls, The resulting shear produces crevasses that curve upstream from the margins toward the center, forming a pattern known as en echelon crevasses. At the terminus of a glacier that is spreading laterally, transverse crevasses may form perpendicular to the flow direction. Crevasses typically penetrate to depths of approximately 25 to 30 meters, which corresponds to the depth at which the overburden pressure from the weight of the overlying ice is sufficient to close the crevasse by plastic deformation. However, in glaciers where there is abundant meltwater, crevasses that are filled with water can penetrate much deeper, potentially reaching the bed of the glacier. Because the hydrostatic pressure of the water counteracts the tendency of the ice to close the crevasse. Ogives are periodic wave-like features that are observed on the surface of some glaciers below icefalls, which are steep sections of the glacier where the ice flows rapidly and is heavily crevassed. Band ogives, also known as Forbes bands, consist of alternating light and dark bands of ice that are spaced at intervals corresponding to the annual flow distance through the icefall. The dark bands represent ice that passed through the icefall during the summer, when the heavily crevassed surface accumulated dust and debris, while the light bands represent ice that passed through during the winter, when the crevasses were covered by snow. Wave ogives are arcuate ridges and troughs on the glacier surface that are also spaced at annual intervals and are thought to result from differences in the rate of compression of ice that emerged from the icefall during different seasons. The distinction between warm-based and cold-based glaciers, which was alluded to earlier in the context of basal sliding, is fundamental to understanding glacier dynamics. Warm-based glaciers, also known as temperate glaciers, have ice that is at the pressure melting point throughout their thickness, except possibly for a thin surface layer that is cooled seasonally. These glaciers are found primarily in mid-latitude mountain regions and in maritime climates, and they are characterized by relatively rapid flow, active basal sliding, abundant meltwater production, and efficient erosion of the underlying bed. Cold-based glaciers, also known as polar glaciers, have ice that is well below the pressure melting point of the bed, and they are frozen firmly to the underlying rock or sediment. These glaciers are found primarily in polar regions and at very high elevations, and they flow almost entirely by internal deformation with negligible basal sliding. Because cold-based glaciers are frozen to their beds, they are generally much less effective at eroding the underlying surface than warm-based glaciers, and they may actually protect the landscape beneath them from erosion. Many glaciers, particularly those in subpolar regions such as Svalbard, the Canadian Arctic, and parts of Scandinavia, are polythermal, meaning that they contain both warm-based and cold-based zones. A common configuration for a polythermal glacier is to have a warm-based interior, where the ice is thick enough for geothermal heat and strain heating to maintain the bed at the pressure melting point, surrounded by a cold-based margin, where the ice is thin and the cold winter temperatures penetrate to the bed. The boundary between the warm-based and cold-based zones, known as the cold-warm transition, is an important feature because it affects the drainage of subglacial water and the patterns of erosion and deposition beneath the glacier. The measurement of glacier velocity, has been accomplished by a variety of methods over the history of glaciology. The earliest measurements, conducted in the mid-19th century, involved placing lines of stakes across the glacier surface and surveying their positions at intervals of weeks or months using theodolites. Modern measurements employ global positioning system receivers, which can be placed on the glacier surface to provide continuous, high-precision records of ice motion. Satellite-based remote sensing techniques, including synthetic aperture radar interferometry and feature tracking in optical satellite images, have revolutionized the measurement of glacier velocity by enabling spatially comprehensive velocity maps to be produced for glaciers and ice sheets worldwide. These satellite measurements have revealed the complex spatial patterns of ice flow in previously poorly observed regions, including the identification of ice streams in Antarctica and the documentation of seasonal and interannual velocity variations in glaciers throughout the world. The flow of glacier ice, despite its extreme slowness by human standards, is a process that is governed by the same fundamental principles of fluid mechanics and rheology that govern the flow of other materials, from lava to honey to the Earth's mantle. The Reynolds number for glacier flow, which is a dimensionless number that characterizes the ratio of inertial forces to viscous forces, is extraordinarily low, on the order of 10 to the negative 13 or less, confirming that glacier flow is overwhelmingly dominated by viscous forces and that inertial effects are utterly negligible. In this respect, the flow of glacier ice has more in common with the slow creep of the Earth's mantle, which drives plate tectonics over geological timescales, than with a rapid flow of water in a river. Even though both glaciers and rivers are driven by the force of gravity and flow downhill in response to the slope of their surfaces. The subglacial hydrological system, which is to say the network of water pathways that exists beneath a glacier, plays a crucial role in modulating glacier dynamics and is itself a subject of considerable complexity. Water enters the subglacial system from several sources: surface meltwater that descends through crevasses and vertical shafts called moulins, basal meltwater produced by geothermal heat flux from the Earth's interior, which averages approximately 65 milliwatts per square meter, frictional heating generated by the sliding of ice over the bed, and strain heating produced by the internal deformation of the ice. The subglacial drainage system can exist in two fundamentally different configurations: a distributed system, in which water flows through a network of linked cavities, thin films, or porous sediment layers at relatively high pressure, and a channelized system in which water is concentrated in discrete channels incised either into the ice or into the underlying sediment. The transition between distributed and channelized drainage configurations has profound implications for glacier velocity. When the drainage system is distributed, water pressure tends to be high and spatially uniform, which reduces the effective pressure at the bed and facilitates rapid basal sliding. When the drainage system is channelized, the efficient evacuation of water through the channels tends to draw down the water pressure in the surrounding areas, increasing effective pressure and reducing sliding velocity. This relationship between drainage configuration and glacier velocity was first proposed theoretically in the 1970s and has since been confirmed by numerous field observations of seasonal velocity variations on glaciers worldwide. In the early melt season, when surface meltwater first reaches the bed, the drainage system is typically in a distributed configuration and the glacier accelerates. As the melt season progresses and the volume of meltwater increases, the drainage system evolves toward a more channelized configuration, and the glacier decelerates despite the continued input of meltwater. The phenomenon of Jökulhlaups, which is the Icelandic term for glacial outburst floods, provides a dramatic illustration of the importance of subglacial hydrology. Jökulhlaups occur when water that has accumulated in subglacial or ice marginal lakes is released suddenly, typically through a subglacial tunnel that expands rapidly as the flowing water melts the tunnel walls. The discharge during a Jökulhlaup can be enormous, sometimes exceeding 100,000 cubic meters per second, which is comparable to the discharge of the world's largest rivers. In Iceland, Jökulhlaups from the subglacial Lake Grímsvötn beneath the Vatnajökull ice cap have been documented for centuries, and a particularly large event in 1996, triggered by a volcanic eruption beneath the ice cap, released approximately 3.4 cubic kilometers of water and caused extensive damage to bridges and roads on the outwash plain below the glacier. The concept of glacier flow can also be examined through the lens of ice fabric, which refers to the preferred orientation of crystal axes within the polycrystalline ice mass. When glacier ice first forms from the compaction of snow and firn, the individual ice crystals are oriented randomly, with their c-axes pointing in all directions with equal probability. However, as the ice is subjected to prolonged stress and deformation, the crystals gradually rotate so that their c-axes become aligned in preferred orientations that are determined by the stress field. In the case of simple shear, which is the dominant stress state in the lower portions of most glaciers, the c-axes tend to rotate toward a single maximum oriented perpendicular to the shear plane. This fabric development is significant because ice with a strongly developed single maximum fabric deforms approximately 10 times more easily in simple shear than ice with a random fabric, a phenomenon known as strain softening or flow enhancement. The development of preferred crystal fabrics in glacier ice has been confirmed through the analysis of thin sections cut from ice cores and examined under cross-polarized light, a technique that was pioneered by the Austrian glaciologist Peter Rigsby in the 1950s and has been refined considerably since then. Deep ice cores from the Greenland and Antarctic ice sheets reveal a systematic progression of fabric development with depth, from random fabrics near the surface to strongly oriented fabrics at depth, with the specific pattern of fabric development depending on the stress history experienced by the ice as it flowed from its site of deposition to the drill site. The presence of impurities in the ice, such as dust particles and dissolved chemicals, can also affect the rate of fabric development and the mechanical properties of the ice, adding another layer of complexity to the already intricate relationship between ice microstructure and glacier dynamics. Glacial erosion, which is the wearing away and removal of rock and sediment by the action of flowing glacier ice and its associated meltwater, is one of the most powerful geomorphic processes operating on the surface of the Earth. And it has been responsible for shaping many of the most dramatic and distinctive landscapes found in formerly glaciated and presently glaciated regions of the world. The capacity of glaciers to erode is directly related to their thermal regime, their velocity, the thickness of the ice, the nature of the underlying bedrock, and the presence of debris at the base of the glacier. And it is generally accepted that worm-based glaciers are far more effective agents of erosion than cold-based glaciers, which, as was noted previously, may actually protect the surfaces beneath them from erosion. The two principal mechanisms of glacial erosion are plucking, which is also known as quarrying, and abrasion. Plucking occurs when blocks of rock are detached from the bedrock surface beneath or adjacent to the glacier and incorporated into the base of the ice. The process of plucking is facilitated by the presence of pre-existing joints and fractures in the bedrock, which provide planes of weakness along which blocks can be separated. The fluctuation of water pressure in cavities on the downstream sides of bedrock bumps is thought to play a critical role in the plucking process, as high water pressures can force water into cracks in the rock, and subsequent reductions in water pressure can allow the ice to refreeze around loosened blocks and drag them away from the bed. The repeated freezing and thawing of water in rock fractures beneath the glacier, a process sometimes referred to as glacial freeze-thaw weathering or frost shattering, further weakens the bedrock and prepares it for plucking by enlarging existing fractures and creating new ones. Abrasion is the process by which rock fragments embedded in the base of the glacier are dragged across the bedrock surface, scratching and wearing down both the tools, which are the rock fragments in the ice, and the bed itself. The rate of abrasion depends on several factors, including the effective normal pressure of the ice on the bed, the concentration of debris at the base of the glacier, the hardness of both the tools and the bed, the velocity of the basal ice relative to the bed, and the rate at which worn tools are replaced by fresh ones. Abrasion produces a characteristic suite of features on bedrock surfaces, the most diagnostic of which are glacial striations, which are parallel scratches inscribed on the rock surface by sharp-edged fragments dragged along by the ice. Striations range in width from less than 1 millimeter to several centimeters and can be traced for distances of meters to tens of meters. They are enormously valuable to glacial geomorphologists because their orientation indicates the direction of ice flow at the time they were formed, providing a record of past glacier behavior that can be preserved in the landscape for thousands or even millions of years. In addition to striations, abrasion can produce glacial polish, which is an extremely smooth, almost mirror-like finish on bedrock surfaces that results from the fine-grained grinding action of silt and clay-sized particles at the base of the ice. Glacially polished surfaces are particularly well developed on hard, fine-grained rock types such as granite and gneiss, and they are a common sight in areas that were recently deglaciated, such as the Sierra Nevada of California, where the polished surfaces of granite domes and valley walls gleam in the sunlight. However, glacial polish is relatively ephemeral in the geological sense, as it is gradually destroyed by weathering and the growth of lichens over periods of hundreds to thousands of years. The erosional landforms produced by glaciers are among the most recognizable features in the physical landscape, and they range in scale from small scratches on individual rocks to enormous valleys and basins that extend for hundreds of kilometers. At the scale of individual mountains, the most characteristic glacial erosional landforms are cirques, arates, and horns. A cirque is a bowl-shaped or amphitheater-shaped depression on the side of a mountain that forms at the head of a glacier, where the rotational flow of the ice excavates the bedrock through a combination of plucking and freeze-thaw weathering at the base and sides of the depression. Cirques typically have steep, near-vertical head walls and gently inclined or over-deepened floors, and they may contain small lakes, known as tarns, after the glacier has retreated. The Bergschrund, which is the crevasse that forms where the glacier ice pulls away from the head wall of the cirque, is thought to play an important role in cirque development by allowing meltwater and cold air to penetrate to the base of the head wall, promoting frost shattering and the removal of loosened rock by the glacier. An arate is a narrow, knife-edged ridge that forms between two adjacent cirques or glacial valleys that are eroding headward toward each other. As the head walls of the cirques retreat through erosion, the ridge between them becomes progressively narrower and more jagged. The Matterhorn, which straddles the border between Switzerland and Italy and rises to an elevation of 4,478 meters, is perhaps the world's most famous example of a horn, which is a pyramidal peak formed by the intersection of three or more arates where three or more cirques have eroded into the same mountain from different sides. The characteristic pointed shape of the Matterhorn, with its four distinct faces separated by sharp ridges, is a direct consequence of glacial erosion from multiple directions over the course of many glacial cycles. U-shaped valleys, also known as glacial troughs, are among the most impressive and easily recognized products of glacial erosion. Unlike the V-shaped valleys carved by rivers, which have narrow floors and steeply sloping sides that meet at a point, glacial valleys have broad, flat floors and steep, nearly vertical walls, giving them a U-shaped cross-section that is unmistakable in the landscape. The transformation of a V-shaped river valley into a U-shaped glacial trough is accomplished by the erosion of the valley floor and the undercutting and steepening of the valley walls by the glacier, a process that may require multiple glacial cycles to complete. The Yosemite Valley in California, which is approximately 11 kilometers long, up to 1.6 kilometers wide, and up to 1,100 meters deep, is one of the most famous examples of a glacial trough, having been carved by repeated glaciations over the past several million years from what was originally a V-shaped river valley of much more modest proportions. Fjords are glacial troughs that have been partially submerged by the sea, forming long, narrow, deep inlets along coastlines in formerly glaciated regions. Fjords are found in Norway, Greenland, Iceland, Scotland, British Columbia, Alaska, Chile, and New Zealand, and they are characteristically very deep relative to the adjacent continental shelf, often exceeding 1,000 meters in depth. Sognefjorden in Norway, which extends approximately 204 kilometers inland and reaches a maximum depth of 1,308 meters, is the longest and deepest fjord in Norway and the second longest in the world. The great depth of fjords reflects the enhanced erosive power of glaciers that were confined within narrow valleys and that received large volumes of ice from tributary glaciers and accumulation areas in the surrounding mountains. Hanging valleys are tributary valleys whose floors lie at a higher elevation than the floor of the main valley into which they open, creating a step or cliff at the junction of the two valleys. Hanging valleys form because the glacier in the main valley, being larger and carrying more ice, erodes its bed more deeply than the smaller glaciers in the tributary valleys, so that when the glaciers retreat, the floors of the tributary valleys are left hanging above the main valley floor. Waterfalls frequently cascade from hanging valleys into the main valley below, and some of the world's most famous waterfalls, including Bridal Veil Fall in Yosemite Valley, which drops 188 meters, owe their existence to this mechanism. Roches moutonnées are asymmetric bedrock hills that have been shaped by the passage of glacier ice over them. The upstream side of a roche moutonné, which face the approaching glacier, is characteristically smooth and gently sloping, having been streamlined by glacial abrasion, while the downstream side is steep and irregular, having been plucked by the glacier as the ice flowed over and beyond the obstacle. The name Roche Moutonné is derived from the French and was coined in the 18th century, though the exact origin of the term has been the subject of some scholarly debate, with some authorities attributing it to a resemblance to the wave-like shapes of fashionable wigs of the period that were smoothed with mutton fat. Roches moutonnées range in size from a few meters to hundreds of meters in length and height, and they are valuable indicators of the direction of past ice flow because their asymmetry consistently points in the direction of glacier movement. Drumlins are elongated, streamlined hills of glacial sediment, or in some cases of bedrock with a veneer of sediment that were shaped beneath a flowing glacier. They are typically ovoid in plan view, with their long axes oriented parallel to the direction of ice flow, and they have a characteristically asymmetric profile, being steeper on the upstream end and tapering gradually toward the downstream end. Drumlins typically range from 100 to 1,000 meters in length, from 50 to 500 meters in width, and from 5 to 50 meters in height, though individual drumlins outside these ranges are not uncommon. Drumlins rarely occur in isolation. Instead, they are found in groups of tens to thousands, forming swarms or fields that can cover areas of hundreds of square kilometers. The Drumlin Field of central New York State, which contains approximately 10,000 drumlins, is one of the largest and best-studied drumlin fields in the world. The formation of drumlins has been debated by glacial geomorphologists for more than a century, and no single theory has achieved universal acceptance. Proposed mechanisms include the erosion of pre-existing sediment by the glacier, the deposition of sediment beneath the glacier in a pattern controlled by variations in subglacial water pressure, and the deformation of subglacial sediment into streamlined shapes by the flowing ice. Recent numerical modeling studies have suggested that drumlins may form as instabilities in the coupled system of ice flow, sediment deformation, and subglacial water drainage. But a complete and universally accepted explanation for drumlin formation remains one of the outstanding, unsolved problems in glacial geomorphology. The rate at which glaciers erode the landscape has been estimated using a variety of methods, including measurements of sediment yields from glaciated catchments. Comparison of bedrock surfaces exposed by glacier retreat with surfaces that have remained ice-free, and cosmogenic nuclide dating of glacially eroded surfaces. Typical glacial erosion rates range from approximately 0.1 millimeters per year for cold-based glaciers and small cirque glaciers to more than 10 millimeters per year for large, fast-flowing temperate glaciers. The Tyndall Glacier in Patagonia, which is one of the fastest eroding glaciers for which data are available, has been estimated to erode its bed at a rate of approximately 38 millimeters per year, which corresponds to the removal of a thickness of nearly 4 meters of bedrock per century. For comparison, typical fluvial erosion rates in mountain settings range from approximately 0.01 to 1 millimeter per year, suggesting that glaciers can erode the landscape at rates that are 1 to 2 orders of magnitude faster than rivers under comparable topographic conditions. The sediment produced by glacial erosion is transported by the glacier in several distinct positions. Superglacial debris is material that is carried on the surface of the glacier, having fallen onto the ice from rockfalls and avalanches on the valley walls above. Glacial debris is material that is carried within the body of the ice, having been buried by subsequent snowfall or having been transported into the glacier through crevasses. Subglacial debris is material that is carried at the base of the glacier, having been plucked from the bed or incorporated into the basal ice through the regelation process. The total volume of sediment transported by a glacier, known as the sediment flux, is a function of the erosion rate, the area of the glacier bed, and the efficiency with which eroded material is evacuated from beneath the glacier by meltwater and ice flow. The sediment deposited directly by glacier ice, without subsequent reworking by meltwater, is known as till, and it is characteristically unsorted and unstratified, containing a mixture of particle sizes ranging from clay and silt to boulders weighing many tons. Till is sometimes described as diamictin, a non-genetic term that simply describes a poorly sorted deposit of mixed grain sizes when the depositional process is uncertain or when a descriptive rather than interpretive term is preferred. Glacial erratics are individual boulders or large rocks that have been transported by glacier ice from their source outcrop to a location where they rest on bedrock of a different type, and they have been recognized as indicators of past glaciation since at least the 18th century. Some erratics have been transported distances of hundreds of kilometers from their source, and by tracing their lithology back to its origin, it is possible to reconstruct the direction and extent of past ice flow. Moraines are accumulations of glacial debris that form distinct landforms in the landscape. Lateral moraines are ridges of debris that accumulate along the sides of a valley glacier, formed from material that falls onto the glacier surface from the valley walls and is carried along by the flowing ice. When two valley glaciers merge, their adjacent lateral moraines combine to form a medial moraine, which is a stripe of debris that extends down the center of the combined glacier. Terminal moraines, also known as end moraines, are ridges of debris that are deposited at the farthest point reached by the glacier, marking the position of the ice front at its maximum extent. Ground moraine, also known as till plain, is a relatively flat or gently undulating sheet of till that is deposited beneath the glacier as the ice melts back, forming a landscape of low relief that may cover extensive areas. The moraines left behind by the great ice sheets that covered much of North America and northern Europe during the Pleistocene ice ages are prominent features of the landscape in these regions, and they have been extensively mapped and studied as indicators of past ice extent and flow direction. The distinction between moraines deposited during glacier advance and those deposited during retreat is an important one in glacial geomorphology. During advance, the glacier bulldozes and overrides any pre-existing sediments, often producing a compact, over-consolidated till known as lodgement till. During retreat, the glacier deposits material as the ice melts, producing a looser, less consolidated deposit known as meltout till or ablation till. Recessional moraines are terminal moraines deposited during temporary pauses or readvances of the ice front during the overall retreat of a glacier, and a sequence of recessional moraines marking successively less extensive ice positions can often be identified in the landscape, providing a record of the stages by which the glacier retreated from its maximum position. The process of glacial abrasion can be further described through consideration of the specific conditions that control its rate and effectiveness. The pioneering theoretical work on glacial abrasion was conducted by Geoffrey Bolton in the 1970s and subsequently refined by Bernard Hallett in a series of influential papers published in the 1970s and 1980s. Hallett's model emphasizes that the rate of abrasion depends critically on the contact force between the rock fragments embedded in the basal ice and the bedrock surface, which is controlled not by the weight of the overlying ice, as was previously assumed, but by the rate at which the ice flows toward the bed and presses the fragments against it. This insight has important implications for understanding spatial variations in erosion rates beneath a glacier, as it predicts that abrasion will be most intense where the ice converges toward the bed, such as on the upstream sides of bedrock bumps, and least intense where the ice diverges from the bed, such as in subglacial cavities. The concept of glacial erosion extends beyond the action of ice alone to include the erosive effects of subglacial meltwater, which can be a highly effective agent of erosion in its own right. Subglacial streams, which flow under high pressure through channels at the base of the glacier, can erode bedrock through both mechanical action and chemical dissolution, producing channels, potholes, and smooth-walled conduits known as night channels when incised into the bedrock. The erosive power of subglacial meltwater is enhanced by the abrasive sediment that it carries, and by the high velocities that can be achieved in pressurized subglacial conduits. In some settings, subglacial meltwater erosion may account for a significant fraction of the total erosion accomplished by the glacier system, particularly in areas where the bedrock is susceptible to chemical weathering, such as limestone and dolomite terrains. The formation of cirques, which was described earlier in this chapter, involves a complex interplay of freeze-thaw weathering, plucking, abrasion, and rotational ice flow that operates over many thousands to millions of years. The classic model of cirque development, which was proposed by William von Lewis in the 1940s and 50s, emphasizes the importance of the bergschrund and the subglacial cavity at the base of the head wall in facilitating frost shattering of the bedrock. According to this model, meltwater penetrates into the bergschrund and into fractures in the head wall rock during the day, freezes at night or during the winter, and the expansion of the ice upon freezing pries loose fragments of rock that are then removed by the glacier. More recent research has suggested that the freeze-thaw mechanism may be less important than previously thought, and that subglacial erosion at the base of the head wall, driven by the rotational flow of ice within the cirque, may be the dominant process responsible for the over-deepening of the cirque floor. The spatial scale of glacial erosion features extends from the microscopic, in the form of individual striations and polish marks, to the continental, in the form of the broad erosion patterns left by the Pleistocene ice sheets. At an intermediate scale, the pattern of glacial erosion within a single valley or mountain range reveals important information about the behavior of past glaciers. The concept of the glacial buzzsaw, which was proposed by the geomorphologists Mitchell and Montgomery in 2006, suggests that glacial erosion effectively limits the height of mountain ranges in glaciated regions by removing rock from elevations above the equilibrium line altitude faster than tectonic forces can uplift it. According to this hypothesis, the maximum elevation of mountains in glaciated regions is controlled not by the rate of tectonic uplift, as might be expected, but by the elevation at which glacial erosion becomes effective, which is itself controlled by the equilibrium line altitude, and therefore by climate. The influence of bedrock lithology on the rate and style of glacial erosion is another factor that deserves mention in this context. Hard, massive, unfractured rocks such as granite and quartzite are generally more resistant to glacial erosion than soft, highly fractured rocks such as shale and limestone. And this differential resistance produces a characteristic pattern of ridges and basins in the glaciated landscape, with ridges corresponding to resistant rock units and basins corresponding to weaker ones. The orientation and spacing of joints and fractures in the bedrock also play a critical role, as these planes of weakness control the size and shape of the blocks that can be removed by plucking. Rock that is densely jointed can be plucked more easily and efficiently than rock that is massive and unfractured, even if the two rock types have similar compressive strength. The relationship between glacial erosion and tectonic uplift is a subject that has attracted considerable attention in the geomorphological literature in recent decades. The concept of a glacial tectonic feedback, in which glacial erosion reduces the mass of a mountain range, causing isostatic uplift of the remaining rock, which in turn exposes fresh bedrock to glacial erosion, has been proposed as a mechanism that can maintain high topographic relief over long periods of geological time. Numerical models of this coupled system suggest that the feedback can produce a quasi-steady state in which the rate of erosion approximately balances the rate of uplift, maintaining a mountain range at a roughly constant elevation over millions of years, despite the continuous removal of rock by glacial erosion. The deposits left behind by glaciers and their meltwater streams extend far beyond the moraines that mark the former margins of the ice, and they include a variety of distinctive landforms and sedimentary features that are collectively known as glaciofluvial or fluvioglacial deposits. Outwash plains, also known as sander in Icelandic, a term that has been adopted into the English language glaciological literature, are broad, flat surfaces composed of stratified sand and gravel that have been deposited by meltwater streams flowing away from the glacier margin. The sediment that forms outwash plains is transported by braided meltwater rivers that emerge from tunnels and portals at the glacier front, and because the carrying capacity of these streams decreases with distance from the ice margin, the grain size of the outwash deposits generally decreases with increasing distance from the glacier, grading from coarse gravel and cobbles near the ice to fine sand and silt at greater distances. Eskers are long, sinuous ridges of stratified sand and gravel that were deposited by meltwater streams flowing through tunnels within or beneath the glacier. Eskers can extend for tens or even hundreds of kilometers across the landscape, and they typically stand several meters to several tens of meters above the surrounding terrain. The longest eskers in the world are found in Finland, Sweden, and Canada, where they were formed by meltwater drainage systems within and beneath the great ice sheets that covered these regions during the Pleistocene. The Punkaharju esker in Finland, which extends for approximately 7 kilometers and stands up to 25 meters above the surrounding lakes, is one of the most famous eskers in the world and has been designated a national landscape of Finland. Eskers are valuable features for reconstructing the subglacial drainage patterns of former ice sheets, as their positions mark the locations of major meltwater conduits. Kames are irregular mounds or hills of stratified sand and gravel that were deposited by meltwater in depressions on the glacier surface, in crevasses, or in cavities between the glacier and the valley wall. When the glacier melts and the supporting ice is removed, the sediment collapses to form the characteristic hummocky topography of kame deposits. Kame terraces are flat-topped benches of stratified sediment that were deposited by meltwater streams flowing between the glacier margin and the valley wall, and they're found along the sides of glacial valleys at elevations corresponding to former ice surface positions. Kettle lakes are circular or oval depressions in glacial outwash, or till deposits that form when blocks of glacier ice are buried or partially buried by sediment and subsequently melt. causing the overlying material to collapse into the void left by the melting ice. Kettle lakes are a common feature of landscapes that were recently glaciated, and they are particularly abundant in the northern United States, southern Canada, Scandinavia, and northern Germany. The lakes of Minnesota, which is known as the land of 10,000 lakes, though the actual number exceeds 11,800, owe their existence in large part to the formation of kettle depressions in the glacial deposits left by the Laurentide ice sheet. Walden Pond in Massachusetts, which was made famous by the writings of Henry David Thoreau, is a kettle lake that formed approximately 10,000 to 12,000 years ago as the last remnants of the Laurentide ice sheet melted from the region. The glacial history of the Earth extends back at least 2.4 billion years to the Huronian glaciation of the early Proterozoic, but the most recent and best documented period of extensive glaciation is the Pleistocene epoch, which began approximately 2.6 million years ago and ended approximately 11,700 years ago. During the Pleistocene, the Earth experienced a series of glacial and interglacial cycles, during which vast ice sheets repeatedly advanced and retreated across the northern continents. At the peak of the most recent glacial maximum, known as the last glacial maximum and abbreviated LGM, which occurred approximately 26,500 to 19,000 years ago, ice sheets covered approximately 32% of the Earth's land surface, compared to the approximately 10% that is covered today. The Laurentide ice sheet, which covered most of Canada and the northern United States, reached a maximum thickness of approximately 3 to 4 kilometers and extended as far south as present-day New York City, Cincinnati, and St. Louis. The Scandinavian ice sheet, also known as the Fennoscandian ice sheet, covered most of northern Europe, including Scandinavia, Finland, the Baltic states, and portions of northern Germany, Poland, and Russia. The British-Irish ice sheet covered much of the British Isles and extended onto the continental shelf. In the southern hemisphere, the Patagonian ice sheet covered much of southern Chile and Argentina, and mountain glaciers were significantly expanded in the Andes, the southern Alps of New Zealand, and the mountains of Tasmania and southeastern Australia. Global sea levels during the last glacial maximum were approximately 120 to 130 meters lower than present, due to the enormous volume of water that was locked up in the continental ice sheets, exposing vast areas of continental shelf and creating land bridges that facilitated the migration of humans and other organisms between continents and islands. The cyclic nature of Pleistocene glaciations is attributed to periodic variations in the Earth's orbital parameters, a theory that was developed by the Serbian mathematician and astronomer Milutin Milankovic, who published his detailed calculations in the 1920s and 1930s. The three orbital parameters that influence the amount and distribution of solar radiation received by the Earth are eccentricity, which is the degree of ellipticity of the Earth's orbit around the Sun and varies with periods of approximately 100,000 and 400,000 years. Obliquity, which is the tilt of the Earth's rotational axis relative to the plane of its orbit, and varies between approximately 21.5 and 24.5 degrees with a period of approximately 41,000 years, and precession, which describes the wobble of the Earth's rotational axis and has periods of approximately 19,000 and 23,000 years. The Milankovic theory, as it is commonly known, proposes that glacial cycles are initiated when the combination of orbital parameters results in reduced summer insolation at high northern latitudes, which allows winter snowfall to persist through the summer and accumulate from year to year, eventually building up into continental ice sheets. The theory was confirmed in a landmark paper published in 1976 by James Hayes, John Embry, and Nicholas Shackleton, who analyzed the oxygen isotope record preserved in deep-sea sediment cores and demonstrated that the dominant periodicities in the ice volume record matched the periods predicted by Milankovic's orbital calculations. However, the Milankovic theory alone cannot fully explain the magnitude and timing of glacial cycles, and additional feedback mechanisms, including changes in atmospheric carbon dioxide concentration, ocean circulation patterns, ice sheet dynamics, and the albedo of the Earth's surface, are required to amplify the relatively small changes in solar radiation caused by orbital variations into the large changes in climate and ice volume that are observed in the geological record. The retreat of glaciers that has been observed over the past century and a half, and that has accelerated markedly since the 1970s, is one of the most visible and widely cited indicators of anthropogenic climate change. The vast majority of glaciers worldwide have been losing mass and retreating since the end of the Little Ice Age, which was a period of modest glacier expansion that reached its maximum extent in most regions between approximately 1600 and 1850. However, the rate of glacier retreat has increased substantially in recent decades, and the period from approximately 1990 to the present has seen rates of glacier mass loss that are unprecedented in the observational record. The World Glacier Monitoring Service, which coordinates the collection and dissemination of standardized data on glacier changes worldwide, has reported that the cumulative mean specific mass balance of the roughly 40 reference glaciers for which long continuous records are available has been negative in every year since 1984. Indicating a sustained and accelerating loss of glacier ice that is consistent with the warming trend observed in global surface temperatures. Between 2000 and 2019, the world's glaciers, excluding the two ice sheets, lost an estimated approximately 267 plus or minus 16 gigatons of ice per year, which contributed approximately 0.74 plus or minus 0.04 millimeters per year to global sea level rise. This rate of loss has increased further in the most recent years for which data are available. The monitoring of glacier change is accomplished through a combination of ground-based measurements, airborne surveys, and satellite remote sensing. Ground-based measurements include the traditional stake and pit method for mass balance determination, as was described earlier, as well as surveys of glacier terminus positions using GPS receivers and theodolites, and measurements of ice thickness using ground-penetrating radar. Airborne surveys, including laser altimetry using systems such as NASA's Airborne Topographic Mapper and photogrammetric surveys using digital cameras, provide high-resolution topographic data for individual glaciers and glacier regions that can be compared over time to determine volume changes. Satellite remote sensing has become increasingly important for glacier monitoring since the launch of the first Landsat satellite in 1972, and modern satellite sensors provide a wealth of data on glacier extent, velocity, surface elevation, and mass change. Satellite gravimetry from the GRACE and GRACE follow-on missions, as was mentioned previously, has been particularly valuable for measuring the mass changes of the Greenland and Antarctic ice sheets, which are too large and remote to be adequately monitored by ground-based methods alone. GRACE measures changes in the Earth's gravity field with sufficient precision to detect the redistribution of mass caused by the loss of ice from the ice sheets, and the data have provided an independent confirmation of the accelerating mass loss from both ice sheets that has been inferred from other methods. The ice, cloud, and land elevation satellite known as ICESat, which operated from 2003 to 2009, and its successor ICESat-2, which was launched in 2018, have provided precise measurements of ice sheet surface elevation using laser altimetry, enabling the detection of even subtle changes in ice sheet thickness over time. Glaciers serve as critically important freshwater reserves for many regions of the world, and the ongoing loss of glacier ice has significant implications for water resources, particularly in arid and semi-arid regions where glacial meltwater constitutes a large fraction of the total water supply during the dry season. It has been estimated that approximately 1.9 billion people, representing roughly 1/4 of the global population, live in river basins where glacial melt makes a significant contribution to streamflow. In the tropical Andes, glacial meltwater provides a substantial portion of the dry season water supply for major cities such as La Paz, Quito, and Lima. And the rapid retreat of tropical glaciers in recent decades has raised concerns about future water availability in these regions. The Chacaltaya Glacier in Bolivia, which was once the world's highest ski area at an elevation of approximately 5,300 meters, has disappeared entirely, having lost its last remaining ice in 2009 after decades of retreat. In Central Asia, the rivers that flow from the glaciers of the Tian Shan, Pamir, and Hindu Kush Karakoram Himalaya mountain ranges provide water for irrigation, hydroelectric power generation, and domestic use for hundreds of millions of people in countries including China, India, Pakistan, Afghanistan, Tajikistan, Kyrgyzstan, Kazakhstan, and Uzbekistan. The Indus River, which is fed in part by glacial meltwater from the Karakoram and Western Himalaya, is the lifeline of Pakistan's agricultural sector, which employs approximately 40% of the country's labor force and produces the food for a population of more than 220 million people. The loss of glacier ice in these mountain ranges is expected to initially increase streamflow as the rate of melting accelerates, but eventually to decrease stream flow as the glaciers diminish in size and produce less meltwater, a transition that has been referred to in the scientific literature as peak water. The concept of peak water, as applied to glaciarized catchments, describes the point at which the annual meltwater contribution from a glacier reaches its maximum value before beginning a long-term decline as the glacier shrinks. The timing of peak water varies from glacier to glacier and from region to region, depending on the size of the glacier, the rate of climate warming, and the sensitivity of the glacier to temperature changes. For small glaciers in many mountain regions, peak water may have already been reached or may be reached within the next few decades, while for the larger glaciers and ice caps of the high Asian mountains, peak water may not be reached until later in the 21st century. After peak water is passed, the reduced glacier meltwater contribution to stream flow will be most acutely felt during the dry season and in drought years, when the buffering effect of glacier melt is most needed. The study of glaciers and their effects on the landscape has a long and distinguished history in the earth sciences, dating back to the early 19th century when naturalists such as Louis Agassiz, Jean de Charpentier, and Ignaz Vanetz first proposed that much of Europe had once been covered by vast sheets of ice. This proposal, which was initially met with considerable skepticism by the scientific establishment, was gradually accepted as evidence accumulated from the study of glacial deposits, erratic boulders, striations, and the distinctive landforms described in the preceding sections of this narration. By the latter decades of the 19th century, the glacial theory had become one of the foundational concepts of modern geology, and the study of glaciers and glaciation has continued to advance through the 20th and 21st centuries, driven by improvements in observational technology, theoretical understanding, and computational modeling. The response of glaciers to climate change is not instantaneous, but occurs over a timescale that is determined by the glacier's response time, which is the time required for a glacier to adjust its geometry to a change in climate and reach a new equilibrium. The response time depends on the size and thickness of the glacier, its flow velocity, and the magnitude of the climate perturbation, and it typically ranges from a few decades for small mountain glaciers to several centuries or millennia for large ice caps and ice sheets. This means that even if greenhouse gas emissions were stabilized at their current levels immediately, glaciers would continue to retreat and lose mass for decades to centuries as they adjust to the warming that has already occurred. Modeling studies have estimated that glaciers worldwide have already committed to losing approximately 20 to 30% of their remaining volume in response to past warming, regardless of future emission scenarios. The melting of glaciers and ice sheets also contributes to sea level rise, which is one of the most consequential impacts of climate change for human societies. The total contribution of glaciers and ice sheets to sea level rise during the 20th century has been estimated at approximately 10 to 15 centimeters, and this contribution is expected to increase substantially during the 21st century as the rate of ice loss accelerates. The Intergovernmental Panel on Climate Change has projected that glaciers excluding ice sheets will contribute between approximately 8 and 16 centimeters to sea level rise by the year 2100 under intermediate emission scenarios, while the Greenland and Antarctic ice sheets could contribute an additional 10 to 40 centimeters or more, depending on the emission scenario and the behavior of marine-based ice sheet sectors that may be vulnerable to rapid destabilization. The physical processes by which glacier ice deforms and flows, erodes the landscape beneath it, transports and deposits sediment, and responds to changes in climate are interconnected in ways that continue to challenge glaciologists and geomorphologists. The movement of a glacier is controlled by the balance between the driving stress, which is determined by the glacier's geometry and the force of gravity, and the resistive stresses, which include friction at the bed, friction along the valley walls, and longitudinal stress gradients within the ice. Changes in any of these factors, whether caused by changes in ice thickness due to altered mass balance, changes in basal conditions due to fluctuations in subglacial water pressure, or changes in glacier geometry due to retreat or advance of the terminus, propagate through the glacier system and affect the rate and pattern of ice flow, erosion, and deposition. The investigation of these interconnected processes requires the integration of field observations, remote sensing data, laboratory experiments, and numerical models, and it is a field of study that has benefited enormously from advances in technology over the past several decades. High-resolution satellite imagery allows scientists to monitor glacier changes across the entire planet with unprecedented spatial and temporal coverage. GPS receivers mounted on glacier surfaces provide continuous records of ice motion with millimeter-scale precision. Ground-penetrating radar systems reveal the thickness of the ice and the geometry of the glacier bed. Borehole instruments record temperature, water pressure, and deformation rates within and beneath the ice. And increasingly powerful computers enable the simulation of glacier dynamics with ever greater realism and detail. As the narration continues, it may be observed that the slow, relentless movement of glacier ice across the landscape, measured in centimeters and meters per day, is a process that unfolds on timescales that are difficult for the human mind to fully comprehend. A glacier that advances at a rate of 100 meters per year, which is a moderate velocity for a temperate valley glacier, will travel 1 kilometer in 10 years, 10 kilometers in a century, and 100 kilometers in a millennium. Over the course of a single glacial cycle, which may last approximately 100,000 years, such a glacier could theoretically travel a distance of 10,000 kilometers, though in practice the glacier's extent is limited by the topography and climate of the region in which it exists. The slow but persistent action of glacier ice on the landscape is analogous, in some respects, to the slow but persistent action of water droplets on stone, a comparison that is apt if somewhat unoriginal. The erosional and depositional features created by glaciers are found across vast areas of the northern hemisphere, from the cirques and arates of the Scottish Highlands to the drumlin fields of Ireland and New York. From the fjords of Norway to the Kettle Lakes of Minnesota, from the moraines of the European plain to the outwash deposits of the Great Plains. These features testify to the enormous power of glacier ice to reshape the land surface, and they serve as a reminder that the Earth's climate has undergone dramatic fluctuations in the geologically recent past. Fluctuations that have alternately covered vast areas of the continents in ice and exposed them to the warmth of interglacial conditions not unlike those experienced today. The glaciers of the Karakoram Range present an interesting anomaly in the global pattern of glacier retreat, as many Karakoram glaciers have been stable or even advancing in recent decades, a phenomenon that has been referred to as the Karakoram anomaly. This anomaly has been attributed to several factors, including increased winter precipitation from westerly weather systems, the unique topographic and climatic setting of the Karakoram, and the heavy debris cover on many Karakoram glaciers, which insulates the underlying ice from solar radiation and reduces ablation rates. The Karakoram anomaly has been the subject of extensive research and debate, and it serves as a reminder that the response of individual glaciers to climate change is influenced by local factors that can produce outcomes that differ markedly from the global trend. The role of glaciers in shaping human history extends beyond their function as freshwater reserves. The advance and retreat of glaciers during the Holocene, which is the current interglacial period that began approximately 11,700 years ago, have affected human settlements, agriculture, and transportation routes in mountain regions throughout the world. During the Little Ice Age, which is generally dated to the period between approximately 1400 and 1850, though the exact dates vary by region, the advance of glaciers in the European Alps destroyed villages, farms, and forests that had been established during the preceding medieval warm period. The village of Le Châtelard in the Chamonix Valley of France, for example, was repeatedly threatened by the advance of the Mer de Glace glacier during the 17th century, and the inhabitants petitioned religious authorities to perform exorcisms and blessings to halt the advancing ice. In Iceland, the advance of glaciers during the Little Ice Age destroyed farmland and contributed to a period of severe hardship for the island's population. The measurement of glacier thickness, which is essential for calculating glacier volume and predicting future changes, is accomplished primarily through radio echo sounding, also known as ice-penetrating radar or ground-penetrating radar. This technique involves transmitting pulses of electromagnetic energy into the ice and recording the echoes reflected from the glacier bed. The depth of the bed can be calculated from the travel time of the echo and the velocity of electromagnetic waves in ice, which is approximately 168 meters per microsecond. Radio echo sounding has been used to measure ice thickness on glaciers and ice sheets since the 1960s, and it has revealed that many glaciers are considerably thicker than their surface topography might suggest, with some valley glaciers exceeding 1,000 meters in thickness in their deepest portions. The ice that currently covers Greenland and Antarctica, and the thousands of glaciers that still cling to mountain ranges throughout the world, represent the remnants of a colder past and the harbingers of a warmer future. Their continued retreat and eventual disappearance, which is projected for many glacier regions under continued warming, will alter river systems, reshape coastlines, and fundamentally change the relationship between human societies and the frozen water that has sustained them for centuries. The study of glacier movement and erosion, which has been the subject of this narration, is therefore not merely an exercise in understanding the physical processes that shape the Earth's surface, but also a matter of considerable practical importance for the billions of people whose lives and livelihoods are connected, directly or indirectly, to the great rivers of ice that still flow, slowly and steadily, across the mountains and polar regions of our planet. And so the ice continues to flow, as it has flowed for millions of years, deforming grain by grain under the weight of its own accumulated mass, sliding imperceptibly over the polished bedrock beneath, plucking and grinding and carrying the fragments of mountains toward the sea. The glaciers of the world, whether they are growing or shrinking, advancing or retreating, are engaged in a process that is as old as the Earth itself, a process that has carved the valleys we live in, deposited the soils we farm, and filled the lakes we drink from. The rates are measured in millimeters per year, the forces in kilopascals, the temperatures in fractions of a degree, and the timescales in centuries and millennia. It is by any measure a slow and patient business, this work of ice upon stone, and it will continue long after the details of its mechanics have faded from the listener's conscious mind, as they may well be fading now, into the quiet and undisturbed territory of sleep.